Good afternoon, everyone. I hope you're doing well wherever you are and keeping well during this difficult time. Today, we're going to go into a little bit of constant voltage loudspeaker systems. It's a bit of a strange subject because the title doesn't really describe what it is too much, but hopefully it'll become clear as we go forward today. So as always, we're going to start off with a little bit of introduction. So my name's Hodgkinson. I'm an application engineer here at Biamp. I'm based in the UK, and I joined Apart in September 2009, and then also with Biamp 9 years before that. So I've been with Biamp as a company for quite some time. Needless to say, please ask any questions in the control panel, and I'll try and deal with them as we're going forward, but there'll also be a section at the end where I ask any questions which you may have. The webinar is also being recorded, so you'll be able to get a copy of that in the next few days, just in case there's some parts that you missed. Also, in the control panel for GoToWebinar, you should find a copy of the presentation as a PDF in case you want to follow along as we're talking. But please raise your hand or ask any questions going forward if there's anything that's not so clear. So as always, starting with a little bit about the corporate overview. Hopefully most of you know who we are and what we do, but just in case, and to clarify any questions, this is where we're at the moment. So the company was founded in 1976, and the headquarters of the company is in Portland, Oregon. But we have a very wide exposure all over the world with R&D centers in North America, Australia, Europe, and in Italy, of course, now. Manufacturing is predominantly done in Portland, Oregon, and in Philadelphia, but we also have outsourced manufacturing in China, of course. Supports and sales services all over the globe. So we have an office in Portland, another in Boston, a London office, Germany, Barcelona, Hong Kong, the list goes on. But we have coverage pretty much everywhere that you need to, and we're represented in over 120 countries worldwide by a group of distributors who really are part of the company as well. So the products that we produce are vast, and the number of different brands that we have within the group now are quite large. So predominantly we're aiming at world-class AV solutions. So this includes things like high-end DSPs with Tessera and Vocia, of course, microphones added on with Parlay, loudspeaker offerings from the DeSono brand community and Apart, and then communication devices predominantly with Devio, Crowd Mics, Moderna, of course, the wireless USB systems. And we now have, of course, unified communication bundles, which make it very easy to use our products or to become part of Teams meetings, for example, or Zoom, and so on. So the markets that we cover, again, are vast, and there's pretty much nothing we can't do. So business and meeting rooms is obviously a big part for us. Nowadays, education is growing for us with the need for remote meetings and mixed format education. Government buildings, of course, sports venues, heavily involved with the community brand and the DSP metric systems, houses of worship, and then with the Apart brand, retail, hospitality, and so on. So there's pretty much everything covered in the verticals out there. So an overview of what we're going to do today. So we're going to start off with some basic electrical concepts, just in case there's any doubts. It's a little bit involved, but it hopefully won't be too tricky for you. But it is necessary so that we have an understanding of why we need to be considering constant voltage systems. Then what does constant voltage actually mean? There's some confusion and difficulty in understanding that, which is fair enough. Then we're going to talk about low impedance systems, high impedance systems, how you actually go ahead and connect loudspeakers and amplifiers when using high impedance systems. Then lastly, measuring impedance, and then a Q&A session. So hopefully that's going to cover any points that you have, but let me know if there's anything else. So some basic electrical concepts. This is really going back to the school days, if you like. So voltage, what is voltage? It's an electrical potential energy between 2 points of an electric field. It's measured in volts and commonly known as V for volts. So in this example, we've got a simple AA battery, and you have 1.5 volts, in this case DC, measured between the two ends of the battery. Current itself is the flow rate of an electric charge within that electric field. So it's denominated as I and is measured in amperes. So in this case, you see the current flowing through the wires which have the voltage potential across it and a load on those wires. Resistance is the amount of opposition of the flow of current by a device or material. So in this case, it's a bulb. It could easily be a resistor within the line of the voltage, if you like. And this is denoted as R and measured in ohms. And when we're talking about resistance, we really are talking about DC signals, so a signal which is across a battery, for example. So those are the three basic ideas of electrical concepts. Then we get into Ohm's law. So this is the electrical triangle here. So V equals IR, or you can say I equals V over R, and so on. So that's a real nice triangle to keep into your mind, if you like. And that gets you out of a lot of problems when you need to think about this stuff. Then we get into the concept of power. So the power is the rate of energy consumption in an electrical circuit. It's denoted as P normally, and is measured in watts. So in this case, the power is reflected by the light energy being emitted from the bulb. It could equally be the sound energy being emitted from a loudspeaker, for example. So that's really going back to basics. And then the power triangle, P equals VI, or I equals P over V. So you can use these triangles to help you out with pretty much everything. Then we've put these all together into what's called an Ohm's law wheel. So you can easily see if I want to work out I, and I have two other variables, I can work out the current. If I want to work out resistance or volts or power, this Ohm's law wheel can become very, very useful for you because it shows all the relationships between power, voltage, current, and resistance. So that's all good. We know those things. But we always talk about this thing called impedance. And what is it? So impedance is the measure of opposition of an AC signal created due to inductance and capacitance. So it's very, very similar to resistance, but it concerns itself with what happens when you apply an AC signal to a circuit. Because the AC signal will react very differently due to the inductance in the wire or the coil of a speaker, for example, and the capacitance. Confusingly, it is still measured in ohms, but it's denoted normally as Z in the system, but you measure it in the same way as resistance. Okay, so it is different, but it's very, very similar to resistance. Okay, and it's quite important to understand that there is a difference between resistance and impedance. So when we start talking about power, we've seen that P equals VI and so on. But delivering power is what we're interested in when we're connecting an amplifier to some loudspeakers and so on. So in this case, I've given three examples of how you could calculate power. So for example, if I produce 100 watts and I draw 1 amp from it, that is, sorry, if I create a circuit with 100 volts and I draw 1 amp from it, that is 100 watts. However, if I generate a 10 volt circuit and I take 10 amps for it, that is also 100 watts. If I have a 1 volt circuit and I draw 100 amps from it, again, it's 100 watts. So no matter which way you dice it, you can get power in very different ways. But you can probably ask yourself, which one of these is better? And for now, let's just understand that it's possible, power is power, and we'll come back to which one is better later on. Okay, so that's enough about the basics, the Ohm's law and the basic electrical theory. So we get to the point, what does constant voltage mean? So an example of this is, for example, a mains distribution strip. So we've all seen these, we're probably sitting right next to some of them right now. You can plug in different devices, mains appliances into this so that you can distribute the electricity to all of those devices equally. Now, when you do plug something else in, like a fan for your office, the voltage on the electrical distribution panel does not change when you add or remove a device. It's always there, it's constant at 220, 240, 110, wherever you are. Equally, you can add another device without affecting the existing devices. So that can be thought of as constant voltage. You can think of audio as the same when you're using high impedance systems. So you can add one or more loudspeakers to the amplifier line without affecting the loudspeakers. But confusingly, when you're looking at an audio signal, the voltage, the AC voltage from the amplifier is of course going up and down all of the time, and that's dependent on the dynamics of the music, but also the level of the amplifier that you have. So if you turn the amplifier level up, the music will get louder, the voltage gets higher. If you turn the volume down, the voltage gets lower, the music gets lower. So the way to think of this constant voltage when we're talking about audio is the voltage is constant at a moment in time. So for a particular moment, the amplifier is constant and will not change depending on how many loudspeakers are connected and what power or impedance each of those loudspeakers is. So it's a little bit of a tricky one. Another way of thinking of it is if the amplifier is being fed with a sine wave, for example, a 1K sine wave, not a great thing to do normally, but if you're doing it as a test, it's a constant signal going into the amplifier, you get a constant signal going out. Now the voltage of that signal coming out of the amplifier will not change when you add another speaker or take some other speakers off. Okay, so hopefully that's clear. It's a bit of a tricky one, but it can be explained. So some misconceptions about constant voltage. Question, is the voltage always there? No, the voltage from the amplifier is lower when the sound volume is low and higher when the sound volume is higher. It also changes with the music dynamics. Question on constant voltage, can I only use ceiling speakers? No, many different loudspeaker types can be used. We have many different ones in our range, pendant speakers, cabinet speakers, and of course ceiling speakers, built-in ones, and some very high powered speakers. So they can all be used with constant voltage systems. Question, constant voltage systems can only be used with low quality sound systems. Yeah, okay, maybe in the past that was true because the quality of the components being used wasn't so good. But nowadays, when you compare some of our speakers with constant voltage and low impedance, you would have a difficult time discerning which was which if you had them back to back, because the quality of the components is so much better now. So some facts about constant voltage. It's often known as 70 volt or 100 volt line systems. So that's how actually people call these things very often. Or they're often called high impedance systems. So there's three different ways of saying the same thing, if you like. And as I just mentioned, if you apply a sine wave to the amplifier input, at full power, you will measure 70 volts, if it's a 70 volt amplifier, or 100 volts AC on the amplifier output when the amplifier is at full power. Also understand there is no standard. So in North America and Mexico, they use a system which is known as 70 volts. It's actually 70.7 volts. It's derived from the RMS of 100 volt peak to peak. That's where it came from. And the reason it is 70 volts is because when you're using a 70 volt AC signal, in most states of North America or the USA predominantly, you don't have to put the speaker cable within a conduit, whereas with mains power at 110 volts, of course, you do have to put it in a conduit. So that obviously saves cost and installation time. In many other parts of the world, in Europe, in the rest of the world, we use 100 volts. There is actually no derivation for this. I think it was just a good figure to use. So it's somewhere between the US version and the mains power that we use. But on top of all of this, constant voltage systems really do make your life easier if you're using many, many speakers and you have long cable distances, for example. Okay, so let's backtrack. We're going to look at low impedance systems. So as a bit of a summary, in general, low impedance electronics is defined as a device having an electrical impedance of less than 1,000 ohms, approximately. Speakers typically have an impedance of 4 to 16 ohms range. They're used in anything from a hi-fi to a large-scale touring system, used where wide frequency response, high SPL audio, or critical listening is required. And these speakers, we've all come across them in our cars, in our hi-fis, in our on-stage backline equipment, and in live sound equipment. So all of these applications very happily use low impedance systems. So the basics, here we have a basic circuit with an amplifier with an 8 ohms rated output, and we have a loudspeaker with an 8 ohms rated impedance. So in this case, the loudspeaker impedance equals the minimum impedance of the amplifier. So this means you get better efficiency. The flow of current between the two is as expected and within the spec of the amplifier. If you add a higher impedance load to the amplifier, it will decrease the efficiency of the whole circuit. If you add a lower impedance to the amplifier than it's rated, it could cause damage to the amplifier because it's going to draw more current than the amplifier can actually source or was designed to source. So ideally what you're looking for is to have the load impedance the same as the rated load of the amplifier. So here we step it up a little bit. We've got 2 loudspeakers. Well, actually, if we change that to be a number of speakers, 6 loudspeakers, it gets a bit more difficult. So in this case, we've got 2 loudspeakers. So we use this formula, 1 over Z total is equal to 1 over Z1 plus 1 over Z2 and so on and so on. And that gives you the impedance of the line in ohms. Now, if all of the loudspeakers have the same impedance, then it's really easy because you just take the impedance of one of the speakers and divide it by the number of speakers. So in this case, the impedance presented to the amplifier is 8 divided by 2, so it's 4 ohms. So that's really quite simple. If you put the loudspeakers in parallel, we've got 4 loudspeakers here of 8 ohms. 8 divided by 4 is 2, so that's a 2 ohm load to the loudspeaker. The more loudspeakers, the lower the impedance. Now, normally you don't get amplifiers which can do much better than 2 ohms minimum load. So you're getting to a limit there when using 8 ohms loudspeakers. So we've got a limited number of loudspeakers possible in this case. We can, of course, connect loudspeakers in series. So in this case, you add the impedances together. So this is a load of 32 ohms with 4 8 ohm speakers in series. So in this case, in series connections, the more loudspeakers, the higher the impedance. However, this is a bit of a difficult situation because if, for example, one of the loudspeakers fails, the whole loudspeaker line will fail. So you lose all of the sound in the complete system. So that's something to take into account when working out how to connect loudspeakers. So here we have a series parallel circuit. So we have 4 speakers in parallel in series with 4 speakers in parallel. So that gives us a total load to the amplifier of 4 ohms. But again, we've got a series circuit in there. So if one chain of this loudspeaker system fails, then the whole system will go down. And also, when you get to wiring this, you'll find that actually it's a little bit tricky to do if you're working on a project with these all over the building. So it's okay, but probably the limit of where you want to go with this. Then we've got a more complex system. So we've got 4 loudspeakers with different impedances, 8, 4, 8, and 16, in series with 3 loudspeakers of 4, 4, and 8. So we could calculate the impedance of this line, but life's too short, really. It's really not worth your bother trying to do this. And this is where high impedance systems can become very powerful for you. So we can make the assumption here that low impedance systems are therefore not suitable for many situations. Now, a warning for you here, it's a bit daunting. There are 3 slides of formulas coming up next, but bear with it, it's not that bad, and they are needed to help your understanding. So the first thing to consider about low impedance systems is the cable size and cost. So if we think about a 600 watt system with a 400 watt load. So this is the formula we've got from the Ohm's law wheel at the beginning. So voltage equals the square root of power times resistance. So in this case, it gives us 48.98 volts for that 600 watt at 4 ohm system. We can then work out the current from the I equals P divided by V. So that gives us 12.24 amps. So in summary, this needs quite a thick and expensive cable to run your loudspeakers down from the amplifier to the loudspeaker or loudspeakers. Also bear in mind that depending on the size and the quality of the cables, with long cables, you're going to get a voltage drop down that cable, and therefore loss of power. So you will probably need to increase the voltage to accommodate that at some point, or the power of the amplifier to accommodate that. It can also be difficult to calculate the total impedance of a line with multiple speakers, as we saw earlier on in the little diagram. So what can we do about this? Firstly, in this case, the current and the cable size and cost, we can try and reduce the current. Okay, that's easy to say, but how do we do that? Secondly, the resistance becomes significant with long cables, and this causes the volts drop down the cable. So one way around this is to increase the voltage, and this means that the volts drop is not so relevant in the grand scheme of things. Lastly, to calculate the total impedance of multiple speakers is quite difficult. So we try and use a system where the speaker impedances are not so relevant and therefore don't affect the overall load that much. So we can look at the concept of using a higher line voltage. So what happens if we increase the line voltage to, for example, 100 volts with this 600 watt system? So using I equals P over V, we get 6 amps. So it's a significant reduction in the current we've used there. The speaker line impedance would then change to be 16.6 ohms, but the power remains at 600 watts. So using P equals V times I, we get 100 times 6 equals 600 watts. Or using P equals I squared times R, we still get 600 watts. So we've maintained the power at 600 watts, but we've increased the line voltage to 100 volts, and we've reduced the current consumption. Therefore, it means we can use lower cost, thinner cables. Also, because the line voltage is higher, the line loss over the cables is less significant as a percentage. So we don't have to concern ourselves too much about that. We've also changed the line impedance so that it's much higher now. So one speaker, when you add one speaker to the overall line, it becomes less significant in the scheme of things. And this is, of course, similar in principle to the mains power distribution that we all enjoy. So this shows you how the mains distribution works. So you have our generating station where they produce quite a low voltage actually at the generation point. And then it's stepped up by a transformer locally. It's sent along the transmission lines at various different voltages, depending where in the world you are and the distance that it has to cover. And then at a substation, it's stepped down. And then at different substations, right down to the primary customer, it's up to about 4 kilovolts. And then locally to your house, there will be a secondary consumer transformer, which takes it down from 4 kilovolts, in my case, to 240 volts, for example. So in that way, we've increased the line voltage, reduced the current, so therefore we can use thinner transmission lines, but we've maintained the power that can be delivered to my house, for example. So that's exactly the same principle as high impedance or constant voltage loudspeaker systems. Okay, so let's look at high impedance systems. We've looked at the theory, let's look at how they actually work. So higher line voltage are used, as we've said, typically 70 or 100 volts. Now, to get this high impedance and to allow us to accommodate the higher voltage, the loudspeakers have a transformer fitted to them, which presents a high impedance load to the amplifier, but still presents a low impedance to the loudspeaker itself. Equally, the amplifier has a similar transformer, which presents a low impedance to the amplifier, but a high impedance to the outside world. Okay, and those transformers normally nowadays are built into the amplifier, but you could still mount them externally if needed. So in such a system, because we have such a high impedance presented to the amplifier from the loudspeaker, all of the loudspeakers can be connected in parallel. So adding one more speaker or 5 more speakers does not actually change the total impedance on the line by that much. High impedance systems are typically used in fixed commercial installations where you have a large number of speakers and maybe some strange ways of connecting them or difficult situations for connecting them. And historically used where wide frequency response is not the primary concern. But as I've said, the quality of products nowadays is so much higher than it was maybe 10 years ago. So high impedance audio systems, an analogy of this is maybe you've got some of these above you in your office right now. So this is a halogen lamp using a 12-volt DC output. So you've got a mains transformer and a power supply changing it to 12 volts DC. DC and AC are the same principle in this case. So it's producing a 12-volt DC signal, which is fed using 2 bus bars across to a number of different lamps. So these are 12-volt DC lamps that you can connect anywhere along that line. And when you connect one lamp with a particular power wattage, it will shine at a particular intensity. If you connect 2 more lamps, they will also shine a particular intensity, but they will not affect each other. So if you disconnect one, it doesn't change how powerful the other ones are, and so on. And of course, you have a maximum number of lamps that you can connect, and that's the same with audio. But importantly, if one lamp fails, if it blows, all of the other ones will continue to work because they're still getting their voltage from the power supply. So looking at high impedance audio systems, here we have a diagram which explains it. So we have our amplifier with a transformer built in. So we can call this a 70 or 100 volt amplifier. Obviously different voltages are available, but these are the key ones that are used mostly around the world. Then we have our transmission line, and we have a loudspeaker with a transformer fitted at the other end. So the amplifier internally and the loudspeaker are actually identical between low impedance and high impedance. It's just the addition of these transformers which change them into high impedance products or compatible with 70 or 100 volts. The great thing about this is that you do not need to think about the impedance when calculating the size of the amplifier that you need. All in all, what you do is you add up the number of loudspeakers and their power. So you add up the power of each of the loudspeakers that are connected in parallel to the amplifier, and that gives you the minimum power of the amplifier that you need. So here we have an example. We have a 70 or 100 volt amplifier, it doesn't matter which at this time. And we have 10 70 or 100 volt speakers. So you just connect all of the loudspeakers in parallel. The number of loudspeakers is only limited by the amplifier power, and you simply add the speaker powers together. So an example with powers shown. So here we have 10 loudspeakers of 5 watts each, so giving us a 50 watt power requirement. So therefore the amplifier needs to be 50 watts of power. And I put in theory here because dependent on how long the cables are, you may need to accommodate that by adding a little bit of headroom power on the amplifier. What we generally do when we're working on systems is we think about a 10 watt headroom, if you like, on this. So in this case, I would probably go with the 60 watt amplifier, because then you're not going to have any problems if the cables are particularly long. Another consideration right here at this design point is, what if the customer comes back to me in 6 months and says, oh, you know what, I really would like to have another couple of speakers on this line somewhere in the room, in the building. So you could, for example, quite easily upgrade the amplifier to a 120 watt design. It would be quite minimal cost now at the head end of the project. But if you tried to change it or add power later on, 6 months down the road, it becomes quite an expensive operation. Whereas if you put a 120 watt amplifier in now, it'll work perfectly with the 50 watt load. And then there's still 70 watts to use for the customer to add more speakers in the future if they need to. Another great thing about high impedance audio systems is you can have different types and different power ratings of speakers. So for example, I've got 6 speakers here in the main room on the top section, which are always playing. So that could be a 60 watt load, whatever it is. It doesn't actually matter what the load is. But then I've got a switch. So you can see on the right hand side, I've got a switch where I can switch on or off the extension speakers into an extension room. So there's 2 speakers in there. So the loudspeakers can be switched without affecting the volume of the others because the other speakers have a high impedance. Equally, the other speakers could be attenuated. So you can see here I've got 1 loudspeaker with an attenuator in the line. So that means that that speaker, when the volume control is at maximum, will be used at its maximum power. But if that's, for example, too loud for that time of day in that room, you can attenuate it just by using a simple volume control. Another way of attenuating a loudspeaker at installation time is by using a different power tap on the loudspeaker. So generally, loudspeakers for installation have multiple power taps. So this one I've shown here is a ceiling speaker, I think, and it has different power taps, for example, at 30 watt, 15 watt, 7.5 watt, 3.75 watt. So that really just changes the amount of the signal coming from the amplifier that will eventually get to the loudspeaker. So you can adjust that, for example, if you've got a 100-volt line going around the building and you have a bathroom where you need to put a loudspeaker, you could tap that down because you really don't want it to be too loud in that environment. So that's something you can do at installation time. This approach also means that future modification and additional speakers become very simple because you can just add the extra speakers onto the 100-volt line without any problem, so long as you don't exceed the power of the amplifier. Then we can introduce or continue with the volume control situation. So here we see the amplifier feeding a volume control and then feeding a loudspeaker. So that's really quite simple. You have a 10-watt loudspeaker, which has the capability of drawing 10 watts from the amplifier. Therefore, the volume control needs to be capable of throughputing 10 watts as well. And the amplifier, of course, needs to be 10 watts or higher. Now, if we move forward, we could have two different rooms here, still fed from one amplifier. So we have 3 loudspeakers, which is a 30-watt total, which means the amplifier needs to be capable of producing 30 watts maximum, or not maximum, minimum, sorry. But then on the top loudspeaker, we've got a 10-watt volume control. And the reason for that is the current or the power going through that volume control is only ever going to be 10 watts. So that volume control can be only 10 watts. However, the lower 2 speakers are connected in parallel. So the power consumption of those could be up to 20 watts. So therefore, the volume control feeding those 2 needs to be 20 watts or higher. But then you connect the feeds to the 2 volume controls together and feed that to the amplifier. So in this case, when you change the volume on either of the volume controls, it doesn't affect the loudspeaker volume in the other section, if you like. So changing the top volume control will not affect the volume in the lowered speakers. If you did this with a low impedance system, you would definitely have some significant change in volume when adjusting one of the volume controls. So you change the volume in the other zone if you were using low impedance. So that's a real big advantage of low impedance. Also, something that people often think is that the volume controls have to be the same power as the amplifier. And that's not the case because the power of the amplifier is split in this case between two chains. So the power of the volume control only needs to be capable of supplying the power to the loudspeakers directly connected to its output side. Another really great feature of the volume controls that we produce, and also the equipment we provide to supply signal to them, is that the volume controls, yes, they have an input and an output, so you can attenuate the voltage. So for example, it could be a small meeting room where when the meeting's happening, they turn the volume down, and when it's not happening, they turn the volume up to hear some background music there. However, this could be problematic if the system is being used for paging, because if the volume is turned down and there's an emergency paging message, or for example, a fire evacuation message, then because the volume's turned down, they won't hear that message. So what we have in a lot of our electronics and inside the volume controls is a 24-volt priority output from the electronics, and that is fed to a relay inside the volume control. So when the paging or emergency situation is active, the 24 volts is applied to the relay, and it actually bypasses the volume control, allowing the audio signal to be fed through the volume control at full level. And once again, this is very, very difficult to achieve with low impedance systems. So whilst it's not a factor directly of high impedance systems, it's something that comes out of it because of the systems that are available around the infrastructure. So some advantages as a recap: high impedance audio system advantages, ease of design and wiring. So you don't really have to concern yourself with impedance calculation. All the loudspeakers are just connected in parallel. It allows the use of thinner and therefore lower cost and longer cables. You can tap each loudspeaker to suit its environment, and you have flexibility in future changes, so adding or removing speakers. It's easy to create volume zones with paging override, and most 70 and 100 volt amplifiers are equipped with background music and paging features to add complexity to your system, if you like. Some disadvantage of high impedance audio systems: they're usually more expensive for small systems. For example, if you just have a couple of loudspeakers, you're paying for a transformer in the amplifier and a transformer in each of the loudspeakers. You do have a reduced frequency response, mainly in the low frequency, but again, advances in transformer technology means that it's pretty negligible nowadays. But if you're really looking for some serious low frequency, then probably not a good idea to go with high impedance. Honestly, poor client and installer perception is still there. So a lot of people say, oh no, I'm not using 100 volts. It's not good enough for me. This could have been true years ago, but nowadays it's definitely worth a listen. So we often do comparisons between low impedance and high impedance, and you really can't tell the difference in most cases. There is an added weight consideration. So transformers in the loudspeakers and the amplifiers, they weigh something. So therefore you have to consider that when you are transporting them or installing them into a rack, for example. Transformers have an insertion loss. So this is a loss due to the power being applied across the transformer coil. Nowadays, you don't really need to concern yourself with that too much. It's quite negligible when you're looking at the overall power consumption. High impedance systems do have a limited power rating. So for example, if you think about a 600 watt system at 70 volts or a 1200 watt system at 100 volts, if you're using the Ohm's law, the impedance is then going to be down around 8 ohms. So then you're getting the same sort of impedance as a low impedance system. So you could think about not using transformers at all unless you need the electrical isolation, of course. So normally 600 watts for 70 volts is a maximum where you need to use low impedance. And that's why you don't see many loudspeakers above 400 watts with 70 volts tappings on them. So moving on to how to connect these devices together. So firstly, connecting loudspeakers. Normally, there are two methods. There probably are more out there, but these are the two key methods. So this is one of the apart loudspeakers, the CMX20DT. So we have a connection point using a push fit connector here. So you literally just strip the wires and push them into the connector. And you see there are a number of wires, and they relate to the different colors, which are denoted on the transformer here. So it shows you how to connect them for a particular power tapping at 70 volts and how to connect them for a particular power tapping at 100 volts. So that's one way of connecting. Another way is where you simply have an input signal from the amplifier, and then you have a power selection switch. So this is one of our pendant speakers. We use the same thing on a lot of the ceiling speakers as well. And also note on this loudspeaker, we have a signal in from the amplifier and a signal out, so like a chain, if you like, which goes through to the next loudspeaker if you're daisy chaining them. So that again really makes this simple to install. So connecting the amplifier to the speaker connector and then select the power using the rotary switch. Also note the transformer table and switch settings here. So we have the same tap position is used for 70 volt and 100 volt, but note you have a different power. So for example, on the yellow connector on the transformer, you have 100 volt at 10 watts, but at 70 volts, it's 5 watts. So that's because of the lower line voltage and therefore the lower current, and resulting in the lower power for that tapping. So it's interesting to note you use the same connection, but actually the power rating really does depend on how you're supplying it, what voltage you're supplying it with. Also note on this ceiling speaker and on the pendant speaker, there is a low impedance position or tap connection and a switch position. And that's so that you can easily connect this in a low impedance system in some projects and then use the same loudspeaker when you're working with 100 volt or 70 volt, for example. So connecting amplifiers, you find that single channel amplifiers or mixing amplifiers generally have a low impedance connection. So you can see here a 4-pin connection with a common, or a ground if you like, and then a connection for 4 ohms, and a connection for 70 volts, and a connection for 100 volts. So you would typically use your pair speaker cable, connect it to the common, and then the required output that you want, depending on what speakers you're using, low impedance, 70 volts, high impedance, or 100 volts line impedance. Multi-channel amplifiers generally have more connections. So for example, here we have a two-channel amplifier, channel 1 on the right, channel 2 on the left. I can connect a loudspeaker, which is low impedance in this case, between the common and the low impedance output on the amplifier. I could equally connect a high impedance loudspeaker, in this case a 70 volt loudspeaker, between the common and the 70 volt output. But equally, if I had a 100 volt speaker, I would connect it between the common and the 100 volt. And because this is a two-channel amplifier, maybe I want to use all of the power of the amplifier. So I have 2 by 240 watts. If I join those two channels together, it's called bridging, and we can produce 240 watts, and I would connect my 70 volt loudspeaker like this. So between the two 35 volt taps on the two channels. So now those two channels are working as one and providing 480 watts at 70 volts to the speaker line. Equally, if I was using a 100 volt line, I would connect my loudspeaker chain between the two 50 volt taps on the two channels. So that's another great feature of multi-channel amplifiers where you can use channel bridging. Another sort of amplifier is what are known as assignable amplifiers. So we have these in the Biamp range. This is a Tessera amplifier, for example. So it has a number of output connectors, 4 output connectors in this case. But in the software for Tessera, you can control how each one of these amplifier channels performs. For example, you can choose independently for each channel whether it's going to be using a 4 or 8 ohm low impedance load or a 70 or 100 volts high impedance load. So you can see in the diagram there, I've chosen each of those for these different channels. And the amplifier just works it out inside on how it's going to deal with this. You can also select the power rating for channel, maximum power per channel, and you can control the level within the amplifier. So this amplifier doesn't actually have any controls on it whatsoever. Everything is done virtually within the DSP system controls or the user controls given from the DSP system. So go back to the question, what voltage should I use? So there are multiple options. There is no standard globally. So 70 volts, or more accurately 70.7 volts, is used in North America and Mexico predominantly. There are some others, parts of Japan, for example, and I'm sure there's other parts in the world where they also use it. And 70.7 volts was used or formulated because you do not need conduit to meet code in most cases. 100 volts is common in Europe. There are other standards. So for example, in some systems, you can use just a 35 volt output or a 50 volt. In higher powered systems, you could use 140 volt and 200 volt outputs. They're less common, but they are equally possible when you need to drive some high powered loudspeakers over long distances. When it comes down to it, the choice of the voltage that you use will depend on your geographical location and the local regulations. For example, in North America, it would be very common to use 70.7 volts. The amplifier facilities will dictate that for you as well, and the power needs of the system. So that will all define what voltage you will need to use. But generally speaking, 70 volts for North America, Canada, and Mexico, 100 volts for most other parts of the world, unless your equipment doesn't follow those needs, and then you need to review that. So going back to the question we had earlier on, which one is better? Unfortunately, it really does depend on the system requirements. So for low impedance, that would be the choice if you have higher power systems, wider frequency range. Maybe you can define it by the application. If it's a rock and roll system, for example, where you need high SPLs, but the cable distances are not so long, and you have many different amplifiers, you would use low impedance. High impedance really comes into its own when you've got a complex setup with many, many speakers, which all need to be connected to one amplifier, long cable runs, and it can really reduce the cable and installation costs. It also lends itself to fixed installation where you have multiple volume zones, for example, paging, and so on. So that's really the summary of high impedance, low impedance, and constant voltage. I thought it would also be useful just to give you a quick 5 minutes on how to measure impedance. So as we've talked about, resistance is the amount of opposition to the flow of current by a device or material used for DC signals. So when you're measuring the resistance, in this case, of the load, you would use a DC multimeter. So a very common multimeter that produces a DC signal. It replicates what the battery would be doing, and it measures the current flow, therefore tells you the resistance in the line. That's all well and good. That's very easy. Most people have one of these multimeters. Where you get into trouble, however, is if you try and use a multimeter for measuring a loudspeaker coil. And the reason you do this is because the loudspeaker is a coil of wire. And if you measure this with a multimeter, you're applying a DC signal across the coil, and the resistance of the wire, the resistance as opposed to impedance, the resistance is very, very low. So you're not going to get a true reading of impedance here. So in general terms, you cannot measure a loudspeaker impedance with a multimeter. So what we recommend is using a true impedance meter. So we have one in the apart range called the Impedance, and this produces an AC signal, an audio signal, which is fed onto the loudspeaker line, and it actually activates all of the loudspeakers connected. So firstly, you can use it to check that your cabling is correct, and you can walk around the installation and listen for this tone. I think it's 300 hertz coming out of the loudspeakers, and you can check that your loudspeakers are all connected in the way that you would expect. Also, in doing that, it can measure measures the impedance of the loudspeaker line. So it's always a good idea to do this before you connect a speaker line to the amplifier. And the reasons for that is if, for example, the installer made a mistake and connected a loudspeaker into the wrong place, or maybe made a short circuit on the cable accidentally, when you connect that to the amplifier and turn it on, it could very easily blow the amplifier. So we very much recommend using an impedance meter to measure the impedance of the line before you connect it to the amplifier. So when you're doing the amplifier measurement, what you will do is leave the amplifier disconnected, connect the impedance meter directly to the speaker line. So don't leave it connected to the amplifier and then connect it. Completely disconnect the speaker line from the amplifier. Measure the impedance, and the impedance will show you what power is expected from the amplifier to drive that circuit. So for example, in your calculations, if you've got a number of speakers and you have calculated that you need 120 watts on the line, but in this case, you're measuring what we can see here, 41.7 ohms impedance. So if I look up on the table, which is on the right side, and by the way, this table is supplied with the Impedance, it's in the lid of the Impedance, so you've always got it for reference. So I can see here 41.7 ohms at 100 volts. It's looking for an amplifier to drive that of 240 watts. So if your calculations state that you expect only 120 watts, you know something is wrong. So either the tappings haven't been set correctly or loudspeakers haven't been connected correctly. So this is just a safeguard so that when you connect the speaker line to the amplifier, it's not going to be damaged from having a too high a load or too lower impedance connected to it, if you like. So that's everything for today that I was going to cover. So a couple of other Biamp webinars if you're interested in them. So on Thursday, September the 10th, we have a webinar titled Considerations when Designing Outdoor Sound Systems. So that's predominantly using the community loudspeakers. So that will be very interesting. And then also 3 webinars, which are the same on September 23rd, October the 22nd, and November 19th. And this is related to COVID-19 and the new normal workplace and how sound masking can help in those applications. Okay, so you can register for any of the webinars by going to biamp.com/training/webinars. And you can also see previous webinar recordings there or get links to them in case you would like to review or relook at any of the presentations that have happened. Okay, so that leads me to the end of the presentation. Thank you very much for attending. I do hope it was useful. If you do have any questions, you can reach out to me directly at ian.hodgkinson@biamp.com. Or as always, you can ask any questions whatsoever regarding Biamp or technology in general to support@biamp.com. And that is monitored 6 days a week. So you normally get a very, very quick response time on that. So I'd encourage you to use that as your email address to contact us regarding technical matters. Thanks again. That concludes today's webinar. Speak to you soon. Bye-bye.